Hey y'all, in this video we're going to talk about aerosols. When you hear the word aerosol, you probably think of, an aerosol can or something that you would spray. And, well, that makes sense. So the definition of an aerosol is a solid particle, so a particulate, or a liquid particle. Those can form in the atmosphere, those can form at the source, but small particles in the atmosphere. You can think about water as a type of aerosol, but it kind of has its own thing going on, so that's why we talked about it separately. When we think about these individual things, generally aerosols are in the troposphere, right? So they're things that are generally sourced at the surface, both kind of human and naturally sourced. But because they're in the layer of the atmosphere that has weather, that has precipitation, they tend to get stripped out fairly quickly. So maybe, a few weeks, 3 or 4 weeks, couple of months, their residence time in the atmosphere is fairly low because generally they either kind of fall out as a response to gravity, right, just because they're heavy, and sometimes they're kind of in the atmosphere because of vertical movements in the troposphere, or they condense further with water droplets and they fall out as a form of precipitation, or they're stripped out, as they get hit by a raindrop. There are a lot of different things that can be aerosols. We're going to talk about maybe four or five different types specifically, but they're actually similar to clouds in a way that once we look at all of the aerosols, they don't all behave the same way. When we look at the group of aerosols, they're pretty variable. Some are liquids, some are solids. Residence time kind of differs, smaller versus larger. And similar to clouds, they don't all do the same thing. Some of them can have negative feedbacks, meaning they have a cooling effect, or some of them can have positive feedbacks, meaning they have a warming effect. So we're going to take a look at, I think, 4 or 5 different types of aerosols, kind of look at what they do, how they interact with the atmosphere, their residence time, and those sorts of things, right? So are they a positive or a negative? Okay, well, let's just go ahead and start talking about a few of these things. So the first one that we're going to talk about is actually pretty important, and it really kind of straddles the boundaries, which is pretty cool. This is sulfate, or what we would call sulfur dioxide. And generally the way that this forms is that something is producing sulfur, and that sulfur in the atmosphere as part of either combustion or kind of natural source will combine with oxygen. It will oxidize and it will form sulfur dioxide. And sulfur dioxide itself is highly reflective. So we'll pause for a second. You think highly reflective, positive feedback, negative feedback? It actually reflects incoming shortwave radiation, which means it's a negative feedback, right? So the more sulfur dioxide there is in the atmosphere, it has a net cooling effect. And actually, this is really interesting. So when we think about sources of sulfur dioxide, the human source actually is tied up with burning coal in particular. There are a few other ways, when you see a cloud of diesel, like someone is rolling coal on you in their diesel truck, a lot of that component is actually sulfur dioxide because there's a high sulfur content in diesel fuel. But we're going to talk about coal. So coal is organic carbon, and as a process of compression of plants over millions of years, most of our coal is 310 million years old, part of that process, sulfur is produced within the coal. So coal has a sulfur content, right? We've got, you can look at a coal mine and it'll have high sulfur coal or low sulfur coal. And kind of mineralogically, it actually has to do with the growth of pyrite in coal. And when pyrite combusts, pyrite is iron sulfide. The iron doesn't end up in the atmosphere, the sulfur does. And so we've got sulfur dioxide kind of coming off of these coal-fired power plants, but the sulfur dioxide is actually causing a negative feedback, meaning it's actually cooling. That's far offset by the CO2 that's coming out of the smokestack. So as I mentioned before, sulfur dioxide in the troposphere doesn't last very long, like a couple of weeks to months. So you've got this coal-fired power plant billowing out sulfur dioxide. Rainwater is stripping that out. So the effects of that reflectivity of that higher albedo tend to be fairly geographically limited close to the source. Now, sulfur dioxide, it has a cooling effect, we just met that, but it also has a pretty significant natural source, and that actually has to do with volcanic eruptions. So when volcanoes erupt, you see all this ash and all this other particulate matter that's given out. A large portion of that's actually water vapor. But if the volcano erupts with enough force, certain types of eruptions will do this. It will actually drive the eruption column past the troposphere into the stratosphere. And so a volcanic eruption has enough oomph to kind of seed the stratosphere with sulfur dioxide. There's no weather in the stratosphere, and so that sulfur dioxide, as it lives in that layer of the atmosphere, it's slowly broken down by solar radiation, this process that we call photochemical dissociation, which means when a photon hit it, it breaks apart, right? Photochemical dissociate, right? So you could break these words down and make them easier to understand. But that means in the stratosphere, it actually has a residence time of a couple of years. A year, kind of significant, it starts to break down. So when we look at volcanic eruptions over history, particularly large gas-charged eruptions, they actually have a significant cooling effect on Earth. So if we look at a diagram that shows incoming solar radiation over time, kind of as a variance from standard, and we look at the timing of large volcanic eruptions, we can see there's a few pretty famous ones, right? So I think 1815, the eruption of Tambora, that's the year that famously people call the year without a summer. So it erupted enough sulfur dioxide that warming was not really happening. A lot of that energy was being reflected back to space, and there were crop failures globally. It was actually kind of a disaster, right? So the year without a summer, it got to the point where there was snow all summer long, crops wouldn't fail, and there was kind of localized famine. There weren't very many people on Earth in 1816, right? There were less than 1 billion people on planet Earth. A lot of people point, if something like that were to happen today, and block that incoming solar radiation, and we had global crop failures, we're knocking on the door of 8 billion people on planet Earth. That would be a big problem, right? That would be widespread famine. But it's all not doom and gloom, right? So again, if you go back and look at these diagrams, remember that it breaks apart in the stratosphere. And so if we look at the effect of these volcanoes and their kind of variation from that standard incoming solar radiation, it goes back up pretty quickly, right? So you've got a really cold year, but it kind of bounces back. So it can cause significant climate impact, but it's fairly short term. Interestingly enough, this is actually one of the things people have talked about for global cooling is, getting into the stratosphere and injecting aerosols of sulfur dioxide artificially to block incoming solar radiation and cool the Earth. A lot of people argue that it's not such a big deal because it does break down fairly quickly. So if you made a mistake, you've only got to pay the price for a year. But that's a big idea, right? And for that idea, that's the kind of thing that happens at the UN, right? Because we're playing with the Earth system. And you really have to get the entire Earth on the same page to realize, like, hey, we've got a problem, right? And that falls into the realm of geoengineering. So actually, in a way similar to sulfur dioxide, although the effects are different, is what we call black carbon aerosols. And these are related to incomplete combustion. So again, coal is implicated here, fly ash and this particulate matter that's pouring out of these smokestacks. That sourced black carbon aerosol is obviously a problem, right? It's black, it has a very low albedo, it absorbs heat, it's a positive feedback, it has an overall positive radiative forcing of about 0.5 watt per square meter. But similar to some of the other things that we've seen, it's really fairly localized. We'll see there can be some problems when the soot kind of goes far afield and starts to pile up. There can be some problems with this black soot, particularly as it kind of falls to Earth, especially in the case of ice, but we'll loop back and talk about that. The next one we're going to talk about is mineral dust. So generally, this is, well, this again has two sources, but we're going to start talking about the natural source. And so if we think about places like the Sahara Desert, well, what happens in the Sahara Desert? Well, there's a whole bunch of sand, right? Lots and lots and lots and lots and lots of sand. And those sand particles are getting blown around by the wind all day, every day. That's what they do. And they roll and they bounce and they're kind of skipping along the ground, this process that we call saltation. And it should come as no surprise. If you look at a sand grain that's been rolling around the desert for, 40,000 years, it's going to become fairly spherical over time, right? Actually, in a way similar to like a river cobble. These little corners and bits and pieces slowly break off each time it's kind of bouncing along. But those little tiny particles actually get carried away as what we call the suspended load or the dust load. And actually, if you look here, you can see this is dust blowing off of the Sahara. It's significant, right? And the Sahara is not the only place where this happens. This happens in the kind of in the Gobi Desert area, kind of north of the Tibetan Plateau. Big deserty areas that don't have a lot of vegetation tend to produce a lot of dust. Similar to what we've seen, these dust particles live in the troposphere, right? So they're kind of exposed to rain and some of the other things we've talking about. So they have a fairly short residence time in the atmosphere, a couple of weeks, couple of months, and their impact is generally geographically limited. But what do you think? Would they be a negative forcing or a positive forcing? So they have a negative forcing, right? I mean, they block incoming solar radiation. They reflect it, right? They've got a high reflectivity. But actually about 20% of the mineral load or the mineral matter in the troposphere is not from natural sources. Can you guys think of a place where we would get mineral dust as a human source? Well, generally it has to do with land use, right? So tilling of the fields, right? Or you can think back to, a catastrophe such as the Dust Bowl, right? In that case, we had tilled all these fields, right? We call it the Great Plow Up. And then it didn't rain, and then the winds came and kind of carried that material away. Or even, a windy day in southern Idaho, the atmosphere is filled with dust that's kicked up from farm fields. And so land use can have a lot to do with it, and again, that's about 20% of the kind of mineral dust load in the troposphere. The last one I'm going to talk about that's a specific source of aerosols is actually biomass burning. This is obviously both human and natural caused. Human-caused forest fires significantly outstrip naturally occurring ones, although there's a lot of moving parts here, right? We have forest fire prevention methods. We put forest fires out. Kind of in the natural system, they just burn on forever. We don't do that. But as you can imagine, especially in Idaho, midsummer into fall, we have wildfire smoke. And that, again, is a negative forcing. So it reflects incoming solar radiation. In this case, you'd really have to kind of parse out whether the forest fire was human-caused or natural-caused. So we've seen all these different sources for aerosols. I want to take a little bit of time in the next video and actually talk about how these aerosols ultimately can affect larger climate patterns, right? Because they don't just exist in a vacuum. Once these aerosols interact with the atmosphere, they can do some strange things. Okay, well, I'll see you then.